How you feeling so far?
Good because there's no test.
Yeah. Good because there's no test. Yeah, it's great attitude. You guys will have a lot of exams in this program. So today we're going to talk about lipids, some of their properties, functions, and the different types of lipid structures that are found in the body and their role in our body's biochemistry. So, but before we do that, just wanted to answer some of the questions I got from yesterday or Wednesday. One question was asking why, someone questions why this lactose molecule was an alpha lactose, and the reason why is because this, again, the anomeric carbon, which is the carbon that is derived from the functional group, it is free in this the lactose and glucose bond. So since this isomer is the alpha isomer, that's why this is called an alpha lactose. Now, when you see sucrose, both of the anomeric carbons are part of the glycosidic bond. So since both of them are part of the glycosidic bond, this cannot be alpha or beta. It's not going to be an alpha or beta since both of the important carbons from the functional group are found in the bond. Does this answer the question that I got on Wednesday? I forgot who asked.
There's me, sir. Yeah, it does.
It does? Okay. All right. So, if you guys were to see this on an exam, maybe, I don't know, what functional group would you say this is, and where might you find the structure? Alkyl? You guys saying alkyl? Okay. And why? What does an alkyl group consist of? Carbon and hydrogens? And so what type, where would this be found? Non-polar amino acid, right? That makes sense to everybody? Okay, correct. So this is an alkyl group. CH, carbon and hydrogens make up alkyl groups, and these groups are non-polar. So this may be a type of question you see on the exam. So that's why I just want you guys to not focus on the amino acid structure. Them like identify them by serine has this, whatever has that. Focus on the functional groups and the categories of the functional groups, and that will significantly help you answer questions on the exam. If a question like this comes. So I was also asked why collagen, even though it has 3 polypeptide sequences, is not a quaternary structure. Because remember, I told you the quaternary structures have 2 or more polypeptide sequences. So collagen, it depends on who you like, what book you read. Some books characterize it as quaternary structure because there's more than 2 polypeptide sequences. But for our purposes, we're going to say that this is a secondary structure because these individual polypeptide chains are so identical that once they're synthesized, they immediately form 3 together and form hydrogen bonds, and they don't go into the quaternary structures that we talked about on Wednesday. So the reason why this is a secondary structure, and it's sometimes called a specialized secondary structure, is because once these polypeptides are synthesized, all 3 of them are very similar, so they don't fold on their own. They just go directly into this rope or braided-like pattern. Does that make sense? Are there any questions about this? All right. Here are the learning objectives. So, as PAs, you guys need to understand the importance of lipids because they are important in our just regular metabolism and our cardiovascular health, and we're going to talk about what role they play in our cardiovascular health. In this lecture, I'm going to give you some examples of how they significantly impact our blood flow And then, so you need to understand how these lipid molecules are implicated in disease states because, again, like I've been saying, this information will help you be able to diagnose your patient's condition and treat them. So here are the two functional group slides that I've been brought up in the previous lectures. So today we're going to talk again about alcohols. We're also going to talk about ester bonds. This is the new bond type that is found in lipid molecules, and then we're going to revisit some other bond types, and that is the amide and the carboxylic acid. So lipid molecules, they include cholesterol, triglycerides, phospholipids, and glycerophospholipids, and fatty acids. These molecules are categorized as one category because they are nonpolar and they're only dissolvable in organic solvents. And they're derived, the word lipids is derived from lipose, which means fat and grease. And these lipid structures are important they're a component of our cell membrane, and they are also important found in some of the fat-soluble vitamins. They're precursors, and they are involved in hormone production, which we know is very important. So how are lipids digested after we consume them? They're mainly digested in the duodenum, where they're broken down by bile salts, and then the bile salts will have a polar and nonpolar region, so they're able to kind of break the highly nonpolar lipids down into smaller molecules. And then pancreatic lipase enzymes will be able to further break down those molecules into single units that are absorbed by the body, and lipids are particularly broken down into free fatty acids and monoacylglycerols. And then those molecules enter circulation, and they're transported to the liver, where the liver will either digest them or further or use them to synthesize other lipid molecules that our body needs for function. So here are the types of lipids. We're going to talk about all of these types except for waxes. So fatty acids are a component of all of the lipid structures that we're going to talk about except for the cholesterol molecule. And this is a line stick representation of fatty acids. So each point represents a carbon molecule here. So in order to determine how many carbon molecules you have, you would just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this fatty acid has 12 carbons, and also this carboxylic acid. Does that make sense? Yes.
Are triacylglycerols and triglycerides, are those terms interchangeable?
Yes, and that's actually a great question, and we're going to talk about that. Yep. So fatty acids are composed of between 12 and 18 carbon molecules. That's the carbon chain, and they also have a carboxylic acid group at the end. Of course, these are not soluble in water, as with the rest of the lipid molecules. You have two types: saturated, where there's only a single bond between all the carbon molecules, and then unsaturated, where there may be double bonds between the carbon molecules. And so here are just the different representation of the structures. We talked about this line angle formula, and this is the formula with all the carbons listed individually. And then here you have a representation where you would just count the number of carbons. So 1, and then since that is a 10 around the second carbon, this would be the first carbon, and there's 10 more CH2s. So you have 1 plus 10, which is 11, plus 1, which is 12. So this is just different representations of how fatty acid looks. So we're going to talk about first saturated fatty acid. Saturated fatty acids, again, have a single bond. We're going to talk about palmitic acid or palmitate, which is found in, of course, palm trees or palm oil. And so it's 16 carbons long here, and this 16 colon 0 represents 16 carbons long, no double bonds. So unsaturated fatty acids have at least one double bond, and when it's only one, it's called a monounsaturated fatty acid. And so saturated fatty acids are typically solid at room temperature. Unsaturated fatty acids are typically liquid at room temperature. And here are two examples of some unsaturated fatty acids.
Sir, I'm sorry, you said so unsaturated are liquid at room temperature?
Yes. Yep. So unsaturated fatty acids can have a conformation of cis or trans. When they are cis, conformed in the cis conformation, that means the functional group, which is the hydrogen atom in this instance, are on the same side, so they're both pointing up. And then, of course, the trans fatty acids, it's the functional groups, the hydrogen atoms are on opposing sides, so one is up and one is down. So with these unsaturated fatty acids, the cis representation is liquid, primarily liquid. Sometimes the trans can be solid, but that's we're primarily going to focus on the liquid formulations of fatty acids when they are found in oils. And so fatty acids, saturated fatty acids, remember these have single bonds, which allows the fatty acid chains to tightly compact against each other, and that's due to dispersion forces, which are like temporary weak attractive bonds because the electrons in the molecules are constantly moving around, kind of creating a positive and negative charge throughout the molecules. So the opposing charges attract each other in the different chains of fatty acids, so they're able to tightly compact with each other, and this is why saturated fatty acids are solid at room temperature. Any question? Yes.
So just to clarify, anything that is cis is more likely going to be a liquid, and anything that's trans is usually solid?
Yes. Yeah. Of course, there are exceptions, but yes, that's the general.
We're talking about the opposite bonds are the in functional group. That's where like the negative charges are coming from. You said the charges kind of attract each other.
Yes, because like the electrons are constantly moving around, and electrons move around in all molecules, but in this case, I don't want to get too deep into chemistry, but you guys remember what dipole is? It's like the separation of bonds. You have positive on one side and a negative on one side. So that's kind of what dispersion forces are. They're creating like a temporary dipole, and that dipole is found throughout the fatty acids of each of the fatty acids. So the opposite charge in each of the fatty acids are going to attract each other. They're just going to like kind of tightly compact on top of each other. Does that make sense? Yes.
And if the more there are, the stronger the dipole.
Yes. Yeah. Yeah.
What requires a significant amount of energy.
Yeah, and higher temperatures, higher temperatures to make liquid. Does that make sense? Any other questions about that? So we have essential fatty acids, which means that we must consume them in our diet, and they include linoleic acid, which is found in nuts, grapeseed oil, and the remainder of fatty acids we can make. So you don't need to know the specific essential fatty acids, but we do need to acquire some, consume them in our diet, and the rest we can make on during lipid metabolism. I'm going to talk about that a little more in So one type of liquid that is a derivative of arachidonic acid is called prostaglandins. These molecules contain an arachidonic backbone. They contain fatty acid molecules. The arachidonic acid backbone is a carbon ring structure, and these molecules also have substituent groups that are important because the substituent groups are like the functional groups, and the particular functional groups on the different types of prostaglandins is what gives them their specific functions and roles. So these molecules are involved in smooth muscle contraction. They're involved in regulating blood pressure and in inflammation. So there are two types that we're going to talk about: prostaglandin E, PGE, and PGF. And you see that they are different based on the group that is positioned off of the ninth carbon, as shown here. So prostaglandin E1 has a ketone group off of the ninth carbon. You see the fatty acid chains. And then prostaglandin F1 has a hydroxyl group off of the ninth position in the 5-ring structure. So what happens is, like, if we were to be hammering a nail into the wall, and we hit our finger with the hammer, arachidonic acid is going to be converted into a prostaglandin, and that is what's responsible for causing the inflammation and pain. And so these are, again, the different types of prostaglandins. You have a new one, prostaglandin PGF2, and this one has the different constituent from the prostaglandin E1 and PGE1 and PGF1. So they're all different based on the substituents off of the carbon molecule, the pentane ring structure. So we would use a non-steroidal anti-inflammatory drug such as naproxen. That is what we would use to treat this condition, and what an NSAID does, it blocks the conversion of of arachidonic acid into the prostaglandins, and it does this by blocking the COX-1 cyclooxygenase 1 enzyme. Cyclooxygenase 1 enzyme is what converts arachidonic acid to prostaglandins. So again, naproxen is what we would use for like a small inflammatory response due to stubbing our toe or hitting our finger with a hammer. And then you have other NSAIDs such as ketoprofen and nabumetone, and those are used for more chronic conditions of inflammation such as rheumatoid arthritis and osteoarthritis. So I mentioned that most of the lipids that we're going to discuss contain, yes?
I'm sorry, sir. So you said it's COX 1 and 2, or is it just 1?
COX
1.
Yes. So I mentioned previously that most of the lipids contain fatty acids, and then there are several different types of lipids that also contain the glycerol backbone. Glycerol is an alcohol structure. We're going to look at the structure in a few slides, but we have triacylglycerols, which are commonly called triglycerides in clinical medicine, as was asked by your classmate. Then we have glycerophospholipids. And you see the general structures of each of them, very similar, triglycerides or tags have the glycerol backbone and the 3 fatty acids. Glycerol phospholipids have the glycerol backbone, and 2 fatty acids also have a phosphate group attached to an amino alcohol on the 3rd position. Sphingolipids are another type of lipids. They also have fatty acids and that phosphate group and amino alcohol, but they have a sphingosine, which is a longer chain alcohol. So sphingolipids have 2 amino alcohols attached, the sphingosine backbone and 1 in the 3rd position. Then we know that steroids, the structure of steroids are completely different from the structure of the previous amino acids, the previous lipids that we've talked about. And so these are categorized as lipids because, like the other molecules, they are nonpolar and they can be dissolved in organic solvents. Steroids have 4 ring structures fused together. 3 of the ring structures are 6 carbon rings, and 1 is the other remaining is a 5 carbon ring structure. So here are again the general structure types of lipids. You have the fatty acid here. Fatty acids are contained in waxes. We didn't talk about waxes, but they're also contained in triglycerides, glycerophospholipids, sphingolipids, and then you have steroids, which have a completely different structure. Any questions about the different structures of lipids?
General level, the relevance of the steroid structure, 6 carbon ring versus 5, is that relevant at our level? You felt that the far right carbon ring has 5 carbons, what's the relevance of that, I guess? Why?
Did I say something else?
Maybe I missed why that is the case.
I'm sorry, what did you ask me?
Sorry, okay, so steroid structure, got the 6 carbon rings and then the 5 carbon ring on the far right. What's the relevance for that, or why is that the case?
Why does it have a 5 carbon ring at the end?
Yes.
I don't know.
Okay.
It's not relevant. It's just the structure of it. Yes.
Similar train of thought.
Can you speak up, please? My ears are old.
Similar train of thought to the amino alcohols that are in the sphingolipids, the glycerophospholipids. Is that just like an amino acid with alcohol?
We're gonna look at that structure. Good question. Yes, we're gonna look at that structure. So you guys might want to, I don't know if I were you, I would just know the different groups found in the different lipids that we talked about. Does that make sense? Somebody say yes, no?
Yes.
All right, first, check on learning. So of the A, B, and C, please, one person for each letter, tell me whether or not there are fatty acids or steroid intermediates found in, for example, A. So what contains a fused 4-member ring system?
Steroid.
Yes.
Steroid.
Say again?
Steroid.
Steroid. Perfect. What contains a long carbon chain? Fatty acid. And what includes a carboxyl? Fatty acids. Right? Does that make sense? Any questions about that? Okay, somebody answer this question for me. Which of the following is not a characteristic of lipids? So one person? Soluble in water. Correct. Lipids are non-polar, so they're not soluble in water. Alright? So, triglycerides, triacylglycerol, tags, commonly that's the different names. These molecules have that alcohol, glycerol backbone, and they have 3 fatty acids that form ester bond with this glycerol backbone. So the carboxylic end of the fatty acid forms that ester bond with the hydroxyl group of the glycerol molecule. And so here is just the line angle tag molecule. Here you see this glycerol backbone in blue, and the fatty acid, you see the carboxylic end of the fatty acid forms a bond with the hydroxyl group, and this is an ester bond. And so this is a specific type of tag. You will never need to know the different name types or even the different fatty acids. Here are 3 steric fatty acid molecules that you guys don't need to know that level of detail, but you can see here the glycerol backbone, the hydroxyl group, the carboxylic end of each fatty acid interacting, forming an ester bond. This is an ester bond, and this is the functional group that was on one of the slide at the beginning of the lecture. And so a water molecule is lost for each of these bonds. So when glycerol and fatty acids combine, they form ester bonds between each of the hydroxyl groups, and 3 water molecules are lost. Any questions? Yes.
Can you explain that one more time?
Yes, so when the glycerol backbone, the glycerol molecule, and the fatty acid interact, the bond type they form is an ester bond, shown here. So there are 3 alcohol or hydroxyl components in the glycerol backbone, OH, OH, OH. Each of these interact with the carboxylic end of each of the fatty acids, and what it does is this forms an ester bond shown here and releases 3 water molecules. Okay. Yes.
Where do they interact? Is it just like everywhere in the body, or is there a specific place where these things become?
Mainly in the liver, like this where this reaction occurs. Any questions about that? So, if you were to see this somewhere on the Thursday after next, when you come to this class, what type of molecule would you say this is? Sure? Yes, you're right. So this is the level of detail that I want you guys to focus on. You don't need to know the name of the structure, but you know the components. You know this is the glycerol backbone, right? The 3 fatty acids, right? And the ester bond formed by the carboxylic end of the fatty acids to the hydroxyl group of the glycerol backbone. Okay, does that make sense? So in our body, or not in our body, but in our body and in most oils, there can be a mixture of fatty acids that form a glycerol molecule, and they would be called a mixed triglyceride. And so just know that there are several different types of fatty acids that make up most of the triglycerides. You don't need to know the name, the carbon length, but it's not always going to be the same fatty acid. That's the take home message. Does that make sense? So, because triglycerides are formed in a reaction that loses water, in order to break that bond, you would add water back, and that is the hydrolysis reaction. and that's achieved by water and the lipase enzyme, or the lipase enzyme. And so what happens is you would add water and the enzyme back to the tag molecule, and it's gonna break that tag molecule into the glycerol backbone and 3 individual fatty acids. Does that make sense? So phospholipids are similar to tags. However, instead of having 3 fatty acid molecules, they also have phosphate group and amino alcohol attached in the 3rd position of the glycerol backbone. So, as I mentioned, glycerol phospholipids, 2 fatty acids, 1 phosphate group, and 1 amino alcohol. So, we know glycerol phospholipids are a component of the cell membrane, and this is kind of how they look when, this is not drawing to scale, of course this is a stick figure representation kind of, but the cell membrane has a polar region and a non-polar region. So what would be the polar region of this molecule? One person loudly.
Alcohol?
Alcohol, the amino alcohol. And what would be the non-polar? The fatty acids, right? So we know this is a component of cell membranes, right? You guys remember that from general biology. Does that make sense? So here are the different types of amino alcohols found in glycerol phospholipids. Again, that little trick that I showed you guys on how I know what type of molecule this is. You see that amine group, the nitrogen, and the CH2OH alcohol. So this is why they are considered amino alcohols. Does that make sense? Yes.
Quick question on the previous slide. Is the glycerol considered part of the hydrocarbon tail, or is it just the fatty acids?
Say that again.
For the hydrocarbon tail, is the glycerol included in that, or is it just the fatty acids?
Just the fatty acids. All right, so for glycerol phospholipids, these are the 3 amino alcohols that are found in glycerol phospholipids. All right. Any questions? Yes.
So you said you're just identifying it based off the alcohol group at the end of one of the chains.
Say that again. Say that again. I'm sorry.
You are looking at these diagrams and deciding it's amino alcohol based off the alcohol group just hanging out at one of the ends of the chain.
It has the structures of it might not always look like it's at the end, but it has all the components. So in this case, they are all at the end, but it has that amino group, which is the positively charged nitrogen, the CH2 and OH. So we know CH2OH is an alcohol, right? And then that nitrogen positive is an amino group. So yes, to answer your question, yes, essentially. Any other questions? So lecithin and cephalin are 2 specific types of glycerol phospholipids that are found in the central nervous system, and they're also found in foods we eat, such as wheat and cereal. And so lecithin contains that glycerol backbone, 2 fatty acids, the phosphate group, and choline. Cephalin contains that glycerol backbone, 2 fatty acids, the phosphate group, and ethanol. Any questions? So, sphingophospholipids are important because they are involved in They're a component of the myelin sheath, and we're gonna talk about the myelin sheath. But these sphingomyelin molecules, instead of the glycerol backbone, they contain a sphingosine, which is a longer chain amino alcohol. In addition to that, they contain fatty acid, like we talked about. All of the lipids that we talked about contain fatty acids except for cholesterol molecule. And these also contain that phosphate group and the amino alcohol as well as shorter amino alcohol. So here is a sphingomyelin structure. This is called mysteric acid. You don't need to know the name, but this is a long chain amino alcohol. See that nitrogen group, long carbon, long alkyl group, and the hydroxyl group. That's why this is an amino alcohol, a long chain amino alcohol. This sphingosine forms an amide bond with the fatty acid that it contains. Amide bond, the NH bonded to a Cl bond, oh right, we talked about this. And then, of course, that phosphate group and the covalent group. So, sphingosines sphingomyelin is very important in a component of white matter of the myelin sheath. We know the myelin sheath protects nerve cells and they aid in neurotransmission. So what happens in multiple sclerosis, the sphingomyelin is lost and it continues to deteriorate. And so that loss of this sphingomyelin in the myelin sheath is what causes the disease to progress, and then scars will form on the neurons. Scars formation is the body's way to try to correct this problem, but unfortunately, the scars make the multiple sclerosis worse because then those scars will inhibit nerve transmission. So, take-home message is that sphingomyelin is a component of the myelin sheath. When the myelin sheath is lost for whatever reason, that is one of the hallmark features of multiple sclerosis. Any questions? All right, so cholesterols, we're moving to the uniquely structured lipids. We have many different cholesterol derivatives. Two types of cholesterol that you guys are going to be very familiar with as clinicians are HDL and LDL, high density lipoproteins and low density lipoproteins. Low density lipoproteins are bad. They're bad, and we're going to talk about why as we go through this lecture. But the pictures on your right represent the cross section of a artery. This is a clear artery. Blood is able to flow with no issues. However, in B, there is significant plaque formation, and you see that there's very limited ability for blood to flow, and this is due to this plaque buildup is due to the cholesterol that this person either attained it is from the diet, or he may have like a genetic predisposure to having cholesterol, high cholesterol levels in the body. And so this buildup of cholesterol, of course, is going to put this person at significant risk of a heart attack or a cardiovascular incident. So steroid nucleus components. So steroid structures contain 3 6-carbon rings and 1 5-carbon ring, all fused together, designated A, B, C, D from right to left. And then there are methyl groups off of the 18 and 19 position of the steroid nucleus. Here's the 18th position, 19th position. And then there are some other functional groups found in the structure of cholesterol, such as the hydroxyl group off of carbon 3 and the alkyl group off of carbon 17. So take home message is if you see this structure, you know that it's cholesterol. You don't need to know the nomenclature system because yeah, I don't need to know that. I had to know and it was painful. I'm glad that I don't have to pass something on painful to you guys. So cholesterol is the most important molecule, one of the most important molecules in our body because it is the precursor to our hormones. It's also a component of fat-soluble vitamins, and however, we need to make sure that cholesterol levels are maintained within a certain range because, like as I mentioned, you have good and bad cholesterol. LDL, low-density lipoproteins, is considered bad cholesterol, and that we want to make sure those levels are low. So we know that cholesterol is found in a lot of different foods. High cholesterol levels are found in animal red meats and things like that, and so we want to limit the amount of foods that contain high level of cholesterols, and that is a recommendation by the American Cancer Society. So if we have a cholesterol level after that is the lab test measures that determines our cholesterol level. If our cholesterol is above 200 milligrams per deciliter, that puts us at risk for having cardiovascular disease. So, if we look at this structure below, somebody please tell me what letter represents the hydroxyl group. A, said A. What about the steroid nucleus? C. C. What about the methyl group? D. And the alkyl chain? D. All right, perfect. Does that make sense? Yes.
Would you be able to draw the steroid?
No drawing of anything. You just need to be able to recognize it. You guys don't have time for that. Any other questions?
So there's no color, like the exam, you're not gonna have the color and identifying, right? That's not, because that's a crutch when you're going through these slides, but there's not gonna be color on the exam.
No, you just would need to know the different functional groups. Just like, I mean, it's not gonna be, you may see something that says, identify the methyl group. I don't know what a methyl group is now. I've been talking about it, for the past 7 lectures. Right? That makes sense? Easy peasy. All right. Any other questions? Yes.
So when you were talking about like LDL versus HDL, is the HDL what's used in like pharmacies and stuff? Like is that what
Is HDL what?
the one with the, you're talking about different types of cholesterol? Is the HDL what's in the pharmacies and stuff like that, or is there a difference? Like,
I'm gonna talk about the different components a little bit later in LDL and HDL specifically. So if I don't answer the question, then please let me know. So bile salts are very critical for lipid metabolism. They're responsible for emulsifying lipids, breaking them down into smaller molecules so they can be digested by the lipase enzymes. These molecules are derivative of cholesterol. They're stored in the gallbladder, and so this picture here is representing like high levels of bile in the gallbladder, and they form gallstones. So this, you could see this, these are huge, probably very painful to the person that had these extracted. So we know that lipid molecules are very nonpolar. You see this one is a cholesterol ester. It has a long a fatty acid, and the cholesterol backbone, or the cholesterol molecule, they're attached together. So all three components are very nonpolar, right? So this can't really travel throughout the body unless it is transported by something that has a polar region with it. So these molecules are transported in the body by lipoproteins. And what lipoproteins do, they surround the cholesterol ester molecule that is on the previous slide. And what they do is they bring that molecule to wherever it needs to go into the body so that it can perform whatever function it needs to perform. Any questions about what lipoproteins do? I'll want you guys to take a 10-minute break. Maybe some of the components of I don't
Or he's like or reaction.
And then for
Made with a B minus. Yeah, right. I thought it was but
yes. No, it wouldn't, because if it's a positive charge, it would. So yeah, that's a good question. Because so you would have to know what your injection is, what is actually like. So if you have you would have to like in order to know definitively, you would have to see all of the specific atoms. So you can't really tell.
you have to see exactly what it's on.
Right, like this, like you wouldn't know. If you see this and you know it's a sphingomyelin, you know that that's the myelin.
Just because of my bond.
Yeah.
Bonds is
Sphingosine. Yeah.
to their family.
Yeah. Yeah. So you would have to know
The entire
the different characteristics of contacts. So here you would know those are ester bonds.
Because of them.
Right. Yeah.
You can't really tell them.
No. Yeah.
So back to the secondary coronary versus the coronary
Well, no. So hemoglobin has four each chain. There's two options. They form secondary and tertiary structures. So then they come together and form tissue. So does that make sense? So that's why, like, because they form tertiary and secondary structures individually. And then there's more than one. That's why it's called versus the collagen. It's just a straight chain in each of them that straight chain. They don't form tertiary structure. They have tertiary. Does that make sense? Yeah, the primary structure. I think so. For sure.
I'm trying to find a difference between the spatial arrangement for the bond arrangement. More so. How is that?
So they're using that's so basically an isomer has more stereoisomer, but a stereoisomer partner like a stereoisomer like us, how the so they have the same atoms together. The arrangement of the atoms are really different. An example was methanol, those have the same how was it? Because the arrangement is different for that the different arrangement is does that make sense?
Because it's different, it's like stereoisomers.
No,
That's kind of hard to
I know, no. It's
yeah. How was it? Where
I still have it up.
so I guess
a lot of great marks out there.
so I saw it has the same molecules that the same one micrometer.
Straightforward. Read these questions. Read the answer. Yes,
It's not gonna be the same atoms with only one being to the letter one. The same atoms, their bond
couple steps beyond just like
exactly. But yes, this and that. Yeah, so that's what it is. They're using each other. So it's kind of, you see how yeah, correct. Tell you why the distinction there. The bond or not.
stall it. Yeah, thank you. I was proud of my hair. Thank you. Appreciate it. And that was I thought that was at the end of the very end of contraction. Or right there, and also both flaps closed before it relaxed. So you could argue it, but in it or on it. So what you gotta ask is, what are you looking at? Are you looking right here or are you looking at right here? If you just messed that up to a pointer, then you're right. If you try to say it's right on that line, just right. You should bring it up to him. I think that's a fair point. Good. I think it's a fair point.
Alright guys, we're gonna get started at so we talked about the total cholesterol level being above 200 as a risk factor for cardiovascular disease. This is just a lipids panel. You guys don't need to know this. You'll learn it next semester or in detail. But this is the types of lipids tested in the lipid panel. We have the total cholesterol, the tags, and the HDL and LDL. HDL, LDL are lipoproteins. The HDL are considered good lipoproteins because they transport triacylglycerol to the liver in order to eliminate them from the body. So that's the body's way of getting rid of the lipids that it doesn't need. And so LDLs use those lipids and build them, and they make them stay in the body longer. So that's why LDL is considered bad cholesterol. Any questions about that? So cholesterol is the precursor to all steroid hormones. Steroid hormones, we know that they include the male and female sex hormones, and they also include hormones that are made in the adrenal glands. The adrenal glands sit on top of each of our kidneys, and they make hormones that are involved in electrolyte balance and in glucose metabolism. Here are some examples of steroid hormones. Take-home message is, see that steroid backbone. They all have different constituent groups off of the molecule, and that is what determines its function. So you won't need to know the specific names or anything. You just need to know how to identify the steroid nucleus. So adrenal hormones, two types, aldosterone, that is what's responsible. It's a mineralocorticoid, and that's what's responsible for maintaining electrolyte balance. And then you have the cortisone. We're very familiar with cortisone, cortisol. Though that is responsible for glucose metabolism and maintaining glucose levels in our body. And here is just the location of the adrenal gland on top of each of our kidney organs. And here are here are the structures of the adrenal glands. Here's cortisone, aldosterone, cortisol, and prednisone. Prednisone is a synthetic form. So again, you see that they're all different based on the constituents that are found around the steroid nucleus. Does that make sense? Don't need to know those structures. So we've talked about fatty acids, triglycerols, prostaglandins, and steroid molecules. Are there any questions about today's session? All right, I will see you guys on Monday. Have a great weekend.